11.5 Alternating series. The convergence tests that we have looked at so far apply only to series with positive terms. In this section and over the next, we learn how to deal with series whose terms are not necessarily positive. Of particular importance are alternating series whose terms alternate in sign. An alternating series is a series whose terms are alternately positive and negative. Here are two examples. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/2 minus 1/6 plus ellipsis equals the sum from n equals 1 to infinity of open -1 closed to the power n minus 1 times 1 over n. And the next line is -1/2 plus 2/3 minus 3/4 plus 4/5 minus 5/6 plus 6 over 7 minus ellipsis equals the sum from n equals 1 to infinity of open -1 closed to the power n times n over n plus 1. We see from these examples that the nth term of an alternating series is of the form a sub n equals open -1 closed to the power n minus 1 times b sub n, or a sub n equals open -1 closed to the power n times b sub n, where b sub n is a positive number. In fact, b sub n equals the absolute value of a sub n. The following test says that if the terms of an alternating series decrease towards 0 in absolute value, then the series converges. Alternating series test. If the series, the sum from n equals 1 to infinity of open -1 closed to the power n minus 1 times b sub n equals b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus b sub 6 plus ellipsis, where b sub n is greater than 0, satisfies number 1, b sub n plus 1 is less than or equal to b sub n for all n, and number 2, the limit as n approaches infinity of b sub n equals 0, then the series is convergent. Before giving the proof, let's look at figure 1, which gives a picture of the idea behind the proof. First, we plot s sub 1 equals b sub 1 on a number line. To find s sub 2, we subtract b sub 2, so s sub 2 is to the left of s sub 1. Then to find s sub 3, we add b sub 3, so s sub 3 is to the right of s sub 2. But since b sub 3 is less than b sub 2, s sub 3 is to the left of s sub 1. Continuing in this manner, we see that the partial sums oscillate back and forth since b sub n approaches 0. The successive steps are becoming smaller and smaller. The even partial sums s sub 2, s sub 4, and s sub 6 are increasing, and the odd partial sums s sub 1, s sub 2, s sub 5 are decreasing. Thus, it seems plausible that both are converging to some number s, which is the sum of the series. Therefore, we consider the even and odd partial sums separately in the following proof. See figure 1. Proof of the alternating series test. And we're back to the text again. Proof of the alternating series test. First, we consider the even partial sums. S equals S sub 2 equals B sub 1 minus B sub 2 is greater than or equal to 0. Since B sub 2 is less than or equal to B sub 1, S sub 4 equals S sub 2 plus open B sub 3 minus B sub 4 is greater than or equal to S sub 2. Since B sub 4 is less than or equal to B sub 3, in general, S sub 2n is equal to S sub 2n minus 2 plus open B sub 2n minus 1 minus B sub 2n close is greater than or equal to S sub 2n minus 2. Since B sub 2n is less than or equal to B sub 2n minus 1. Thus, 0 is less than or equal to S sub 2, which is less than or equal to S sub 4, which is less than or equal to S sub 6. Ellipsis, which is less than or equal to S sub 2n, which is less than or equal to ellipsis. But we can also write S sub 2n equals B sub 1 plus open B sub 2 minus B sub 3 close minus open B sub 4 minus B sub 5 close minus ellipsis minus open B sub 2n minus 2 minus B sub 2n minus 1 close minus B sub 2n. Every term in parentheses is positive, so S sub 2n is less than or equal to B sub 1 for all n. Therefore, the sequence open bracket S sub 2n close bracket of even partial sums is increasing and bounded above. Therefore, it is therefore convergent by the monotonic sequence theorem. Let's call its limit S, that is the limit as n approaches infinity of S sub 2n equals S. Now we compute the limit of the odd partial sums. The limit as n approaches infinity of S sub 2n plus 1 equals the limit as n approaches infinity of open S sub 2n plus B sub 2n plus 1 close equals the limit as n approaches infinity of S sub 2n plus the limit as n approaches infinity of B sub 2n plus 1 equals S plus 0 equals S. Since both the even and odd partial sums converge to S, we have the limit as n approaches infinity of S sub n equals S. See exercise 11.1.92a. And so the series is convergent.